Today we're going to talk about functions, and there are two types of functions we're going to deal with today. And the first one is called a one-to-one. A one-to-one function is when the domain part matches up with one part of the range. So look at how the 1, 2, and 3 match up with something in the range. Now something in the range may not always match up, but at least the domain does. The other side of that is if we have every part of the range matches up to one part of the domain. So if we talk about the range matching up, it's called an onto. If everything matches up, one thing of every domain and one thing of every range, then we have both types of functions. So what we want to do is identify domains and ranges, and whether they're ontos or one-to-one functions. So our first example is state the domain and range of each relation. So to state the domain would simply be all the x values. So if we look at the x values, we have a -6, we have a -5, we have a -3, -1, and a 6. So those are all the domains or x values. Now if we look at the range are the y values. So the y values, we have a -1, we have a -9, -7, +7, and we have a -9 again. But because we already have it in the range, we don't write that. So this is our range, so we don't want to repeat any of the elements. So there's our domain and range. So the next type of problem is we look at whether we have an onto or a one-to or both. And so what we're going to look at are the domain. Do they match up with everything on the range? And they do match up. -3 does, -2, -1, 0, and 1. And they match up with everything. Then we look to see if the range matches up. Well, there isn't. 8 doesn't match up with anything. Since it doesn't match up with anything, it is not an onto, so it must be a one-to-one. And that. Okay, so other types of relations, we have what's called the discrete relation, which means when you have dots like this, because you have a distinct individual basically domain or x values, which these do, you have what's called a discrete. Now, if those dots are connected and they go on forever, are continuous, similar to the line, then we have what's called a continuous relation. And we can always tell whether a function is a function by the vertical line test that we're going to use. So let's look at this real-world example and see if we can identify those elements. So the first thing we have is the graph shows the length of Tour de France in kilometers from each 2000 to 2009. We want to know if it's a discrete or continuous. Well, it stops at a certain point, and it's just dots. So this is a discrete relation. So that answers our first question. Our next question is, does the graph represent a function? So what we want to do is we want to see if any of the x values repeat. That means if I do a vertical line down from each point, do I run into any other points? And I do not if we go through all the dots. So we do have a function. So it is a function. And these answers are also highlighted here, right here, for you to go back over. Now we're going to look at graphs of relations and answer the same kind of questions once we've created the graph. So we want to graph this function right here, or this equation, I mean. And so we're going to make a table of values. So I'm going to have my x values and my y values. If my x value, let's say I put a 0 in, and I do put 0 into the function, I would get 1/2 times 0 minus 3, which would give me the answer of -3. If I put a positive number, let's say put a 1 in, I would get 1/2 minus 3, which gives me a -2.5. And then I'll put a negative number in. Let's put a -1 in. If I put a -1 in, I will have a -1/2 minus 3, which gives me a -3.5. Once I have 3 points, I can create a graph. So I'm going to go ahead and draw a graph out. 0, -3 is our first point. Our second point is 1, -2.5. So I go 1, -2.5 is somewhere right in here. And if I go a -1, I would go down a -3.5, which is right in between. You notice that they form a line. So we form a line, and the line is continuous because we can keep giving x values as y values. So to answer our question, do we have a 1-to-1 onto or both? Well, because one value of the x matches up with one value of the y, so x does match up with y, we have a 1-to-1, and nothing is left out, so it's really both a 1-to-1 and an onto. So it's both. Then we want to know if it's discrete or continuous. Well, because they all form a line and it goes in both directions, it is also continuous. So we've answered the questions by using our graph to be able to determine that. Next type is evaluating functions. Evaluating functions means finding the value. So when we have a function and we have a function notation, this means we're going to take the 6 and we're going to put it for the x, that's what exactly, and then we're going to do the same thing into this function. So f of x is really taking f of 6, and I'm going to change the x to a 6, or substitute. So I put the 6 in, minus 8. So if I do the math, that's 36 times 2 is 72, minus 8 would give us 64. So f of 6, that means the function of 6 equals 64. So when I'm putting in my x value of 6, I get 64, which is really the y value. So technically, my answer is 64, because x is 6, and when we get our answer, we get y. So the part that we need to understand about this is that when we have our function, y equals whatever the f of x value is. Let's go through that same process down here. On the next one, I have 2y as our x. So I have f of 2y, and I'm going to substitute 2y for x. So there's my substitution, minus 8. So if I do the math, this is going to be 2 times 4y squared. And that's just doing the square part. Now I multiply, because I'm doing order of operations. So this will be 8y squared minus 8. And because those are not like terms, we can't go any further. So that's what the f of y equals, or the f of 2 of y. So let's go through the same process with the 4a with another function. So I'm going to substitute. So I have g 4a. I'm going to substitute where I see an x. So I have a 0.5 times 4a squared. Squared. And I probably did this wrong. That really should be a 2 over here. And then I have a minus 5 times 4a and plus 3.5. So if we go through the math of this, 0.5 times 4a squared is 16a squared. And this will be minus 20a plus 3.5. And then a half times 16 will be 8a squared minus 20a plus 3.5. So all I've done is order of operations and combine like terms. And these cannot be combined. So this ends up being my answer for G of 4 of A.